Good evening. I welcome you all for the Week 11 live interactive session for the course Chemical Reaction Engineering 2. Now, let's get on to the session. Let's have a brief recap of the lectures of Week 12. So, the lectures of Week 12 had 5 lectures, lecture 56 to 60. Lecture 56 was on reactor diagnostics and troubleshooting. Here, the residence time distribution for CSTR and PFR under normal, bypassing and dead volume conditions were discussed. This was followed by lecture 57, where modeling of non-ideal reactor was discussed. Here again, there was a discussion on PFR and CSTR in series, where the RTD of the PFR and CSTR in series was discussed, and and it was found to be that whether it is a PFR followed by a CSTR or CSTR followed by a PFR, the RTD curve looked the same. However, the performance of the reactor would vary owing to the conditions like mixedness, etc. As RTD does not give a complete information on the mixedness. The next lecture was on modeling of non-ideal reactor again. Here, RTD for diagnosing was discussed. Where the mixing, bypassing and dead volume, what is the exit conversion were all discussed when kinetics is known. And then predicting the conversion. So for predicting the conversion, the RTD alone does not help. There requires a model and kinetic information to identify the exit conversion. So different models available like zero adjustable parameter model having two subdivisions of segregated and maximum mixedness model were all discussed. And the limitations of RTD function, where we have information on time or how much time the material spends inside the reactor. However, there is no information about mixing or exchange between the molecules that controls the reactor behavior, except for the first order reaction uh, was discussed. This was followed by a discussion on macro and micro mixing, where where in macro mixing there is no mixing at the molecular scale. However, in case of micro mixing, the molecules have a microscale interactions, molecular level interactions and mixing between the different molecules. And then the certain definitions like globule, macrofluid and microfluid were all discussed. The lecture 59 was on again non-ideal reactors. Here zero parameter model, especially the segregation model, was discussed for CSTR, PFR and laminar flow reactor. And the final lecture was again on non-ideal reactor with zero parameter model. Here the maximum mixedness model was discussed. And then there was a discussion on multiple reactions, where both the segregation and the maximum mixedness model were all discussed. Now let's get on to the practice assignment for the week 11. Identify the E curve for CSTR with bypassing from the following. Here we are given 4 curves. So we have to identify which one of these 4 curves matches the RTD function, the residence time distribution curve of a CSTR that has bypassing. So if we look into the curve A, so there is a we can find a curve with a exponential decay starting after a certain time t. In the second curve, there is an exponential decay which starts from time t equal to 0. Here and then in the third and then there is an exponential decay which takes a very long time for a complete decay. Whereas in the third curve, curve C, we can observe that uh, you know there is an exponential decay starting from time t equal to 0. However, the exponential decay falls drops rapidly. I mean, the uh, it reaches the decay reaches closer to 0 at a shorter time. And then the final option D shows a curve where there is a rapid fall uh, initially at time t equal to 0, and then there is a exponential decay with time. So which of these matches for a bypassing? So whether it is option A or option B or C or D, which of them matches the CSTR with bypassing? We know that in the case of bypassing, a certain amount of fluid without much interactions comes out rapidly from the reactor. So we have to keep that in mind and then see how the curve looks like. So the answer for this is the option D. Here we can find that there is a initial rapid fall at time t equal to 0. So this portion of rapid fall actually corresponds to the bypassing, because that fluid, it comes out of the reactor almost in a very short time. That is why there is a rapid fall in the RTD curve. And then this is followed by a exponential decay, which is typical of a CSTR. So CSTR, the E curve or the RTT curve is an exponential decay curve. However, when there is a bypassing, there will be a rapid fall initially, which is very close to time t equal to 0, and then there will be an exponential decay. So if we look into the comparative curves of an ideal CSTR, and then a CSTR with bypassing and the CSTR with the dead volume, we could look into the curve. So for an ideal CSTR, so the E curve starts at E of t equal to 1 by tau, and then there is an exponential decay. Whereas when there is a bypassing, the E curve starts at 1 by tau SD, and then it falls rapidly to, sorry, I'm sorry, when there's a bypassing, the E curve rapidly falls down when time closer to 0 to a point of V square SB by V into V naught, where VSB is the volumetric flow rate of the bypassing fluid. Okay, so and then there is an exponential decay. Whereas when there is a dead volume, so the dead volume, the CSTR with the dead volume will have a tau which is smaller than that of the space time of a ideal CSTR. So 1 by SD will have a higher, since tau SD is less than tau. So 1 by tau SD will be greater than tau. That is why the E curve starts at a little higher value, and then it falls comparatively faster compared to an ideal CSTR. So this is how the comparative curves of a CSTR with ideal CSTR, a CSTR with the bypassing, and the CSTR with the dead volume looks. Now let's proceed with the question number 2. Suggest a combination of ideal reactors such as one with the bypassing, dead volume, multiple mixing zones, or intercirculation for each of the following real reactors in the figure that had the following RTT curves. So we have been given 4 different types of RTD curves, and for each of these curves we have to identify a combination of ideal reactors that would produce such an RTD curve. So they have given some F theta curve, E theta curve, F of t curve, and E theta curve again. So now let us look into the combination of ideal reactors for the flow for each case. Case number 1, if you look into the F theta curve, it starts at at a point of theta equal to 0.5, which is well less than that of theta equal to 1. Theta is nothing but t by tau, where tau is a space time. So this starts at a point of theta less than that of 1. And then it rapidly reaches, the f of theta rapidly reaches 1. So what kind of curve this is? So here f of theta reaches 1 at theta 0.5, which is less than 1, where theta is t by tau. So this is similar to a situation where a PFR with a dead volume can be considered, because since there is a PFR, for PFR we can find a spike in the case of E theta curve, and also the curve goes rapidly to 1 in F theta curve as well. But this happens in case of our ideal PFR at theta equal to 1. However, here we have theta equal to 0.5. That means this is a case where we have a PFR followed by a dead volume. Okay. Now let's move on to the, so this is how the curve looks like. So there's a PFR and there's a dead volume which has to be accounted for this, since it starts at a point of 0.5 instead of 1. Now let's look into the curve 2. Here we have a E theta curve where we can find one spike at a value very close to the origin, that is at value of theta very close to 0, and then we can find another spike or a peak at theta little larger than 1. So what is that this type of curve can be correlated to? So here E theta has two peaks, one at the very beginning of theta while other after theta equal to 1. So this again, so here E theta curve we find two spikes. That means something of PFR can be correlated with. So this can be modeled as a PFR with bypassing. So here the first spike can be corresponded to a bypassed fluid, while the second spike, which takes a longer time than theta equal to 1, because the remaining part of the fluid takes a longer time and the volumetric flow rate of the remaining part of the fluid is reduced. So it takes a time greater than that of tau, and that is why we have the second spike at theta greater than 1. So this can be modeled as a PFR with bypass. So some fluid is entering, and initially it has some bypassing. That is why we have some bypass where some volumetric flow rate of VB just goes to the output, and then the remaining part of the fluid passes through the PFR. Okay, this can be modeled as a PFR with a bypassing. Now let's look on to the curve number 3. So curve number 3, it is again a f of t curve. So f of t curve where it is having initially there is one jump here at some point of time, and then the f of t is maintained, and later there is a second jump at some other time t2 greater than t1, and then the value is maintained constant. So how can we model this? So as I said, so here the f of t shows first jump at some time t1 and then stays at it, and then shows a second jump at time t2. So this situation can be considered as two PFR connected in parallel, with one of them having lower space time than that of the other. Right? The output from the PFR having the lower space time, so it comes out fast. So since it is having, the particular PFR is having a lower space time, the fluid entering that will come out faster compared to that. So the output of that can be observed first, and that is shown as the first jump in the f of t curve, and then it maintains the value. And once the space time of the second PFR is reached, the output from both the PFR can be observed, and thus it reaches a second jump. Here this jump, and then it is maintained. So this can be modeled as two PFR in parallel, with one having a lower space time, this shorter PFR, and the other having the higher space time. Okay. Now let's look into the final curve. So this curve, there is an initial spike and then the E theta, this is again an E theta curve, there is an initial spike and then the value drops down, and then after a certain point of time we find a spike and an exponential decay. So how can we model this? So here the first spike can be modeled as the bypass, okay, in a PFR, and then followed by the actual output from the PFR, so which is given by the second spike, and then the exponential decay, which is a which corresponds to a CSTR. So the initial first spike corresponds to the bypassing, and then the second spike corresponds to this line. This corresponds to that of the PFR output, and from there the CSTR output comes into picture with an exponential decay. So this is how the system will and that can be modeled. A PFR followed by a CSTR with the initial, before entering the PFR, there is some bypassing of the fluid. Now, next question. An RTD experiment was carried out in a non-ideal reactor that gave the following results. So, some RTD experiment was, conducted in a non-ideal reactor and it gave certain E curve values. So, E of t was 0 for time less than 1 minute, and then E of t was 1 minute inverse for, here there is a typo error. It's actually less time between 1 and 2 minutes. Okay, yeah, let's get on. So the value of E of t was 1 minute inverse for time between 1 and 2 minutes, and then again the E of t was equal to 0 for time greater than 2 minutes. Now we have to calculate certain things. So the first question is, what are the mean residence time Tm and variance sigma square? The second question is, what is the fraction of fluid that spends a time of 1.5 minutes or longer in the reactor? And then the third question is, what fraction of fluid spends 2 minutes or less in the reactor? And the final question is, what fraction of fluid spends between 1.5 and 2 minutes in the reactor? So we have been given some non-ideal reactor and its RTD values, where the time range is between 0 to 1 minute, and then 1 to 2 minutes, and then 2 minutes to infinity time. Now let's see how to proceed with this question. So for the first question, so we know that mean residence time is given by integral 0 to infinity t into E of t dt divided by integral 0 to infinity E of t dt. So the denominator is nothing but equal to 1. The area under the E curve is always equal to 1 for the entire range. So you will get the mean residence time is equal to integral 0 to infinity t into E of t dt. Now for this question, how should we handle? So we have been given 3 different range. So we have to split this integral. So the mean residence time is given by integral 0 to 1 t into E of t dt plus integral 1 to 2 t into E of t dt plus integral 2 to infinity t into E of t dt. Why are we splitting into 3? Because we have been given E of t values in 3 different range. One is time less than 1, and then the next is time between 1 and 2 minutes, and then after 2 minutes. So that is why we split it into 3, and then we have to incorporate the values. So for the first case where time is 0 to 1, the E of t value is given as 0. So if we substitute in the integral, so the overall value will be 0. And then from 1 to 2, the E of t value is given as 1. So you will have integral 1 to 2 t into E of t is 1 so into dt plus integral 2 to infinity t into e of t dt. Here again the e of t value is equal to 0. That means the total value is 0. So we only have this range of, there is a specific value only for this range of 1 to 2. So that means the mean residence time is given by integral 1 to 2 t into dt. So integration of x is it is x square by 2. So here it is t square by 2 within the range of 1 to 2. So and then applying the limits, you have 2 square minus 1 square divided by 2. That is nothing but 4 minus 1 by 2, that is equal to 3 by 2. So the mean residence time is nothing but 1.5 minutes. Okay. Now we have to find out the variance. So variance is given by integral 0 to infinity t square into e of t into dt minus tm square. Okay. So here again, when we split this integral between the three different ranges, you will have integral 0 to 1 and then integral 1 to 2 and then integral 2 to infinity. And in all, wherever we have integral 0 to 1 and 2 to infinity, the value of e of t is 0. That means that entire integral goes to 0. So what we are left with is integral 1 to 2 t square into e of t dt minus tm square. So integral of t square is t cube by 3. And then applying the limit of 1 between 1 and 2. And then tm square is nothing but 1.5 square. So once we apply the limit, so it is 2 cube minus 1 cube by 3, that is 8 minus 1 by 3 minus 1.5 square, which is nothing but 2.25. So you will end up with a variance value of 0.083. Okay. Now we have to proceed to the question, part B of this question. What is a fraction of fluid that spends a time 1.5 minutes or longer in the reactor? That means, which is nothing but 1 minus f of 1.5, right? So f of 1.5 means it is 0 to 1.5 e of t dt, whereas 1 minus f of 1.5 is integral 1.5 to infinity e of t dt. Here again, we have to split the integral because we have been given e of t in three ranges. So here we are, the first range of 0 to 1 does not come into picture at all, because we have to find out the fraction that spends the time between 1.5 minutes. That means you will have the range of integral 1.5 to infinity e of t dt. Now that is nothing but integral 1.5 to 2 e of t dt plus integral 2 to infinity e of t dt. So integral 2 to infinity e of t dt is 0. So what we are left with is integral 1.5 to 2 e of t dt. Right? And e of t value is 1. That means integral of dt is t. Right? So so t within the limits of 1.5 to 2, that is 2 minus 1.5. So you will find out that the fraction of fluid that spends a time 1.5 minutes or longer is 0.5. So 50% of the fluid fraction, it spends a time over 1.5 minutes. Okay. Now let's get on to the part C of this question. Now in the part C, they have asked for what is the fraction of fluids that spends 2 minutes or lesser in the reactor. Okay. So here it is f of 2. F of 2 means it is integral 0 to 2 e of t dt, because they have asked for fraction. So f gives the fraction of fluids that spends a particular time. F of t gives fraction of fluid that spends a time t in the reactor. So that means here it is f of 2 means integral 0 to 2 e of t dt. So again here splitting the integral between 0 to 1 and 1 to 2, right? So 0 to 1 and 1 to 2. So 0 to 1 it is again 0. So it is just integral 1 to 2 e of t dt. So we know e of t value is 1. That means substituting that, you will end up with the f of 2 as the fraction of fluid that spends time less than 2 minutes is 1. That means the entire fluid just spends the time less than 2 minutes in the reactor. And then by 2 minutes, the entire fluid comes out of the reactor. This is what it means. Final question. What is the fraction of fluid that spends the time between 1.5 and 2 minutes in the reactor? That means it is f of 2, f of 1.5 to 2. That is f of 2 minus f of 1.5. That is nothing but equal to integral 1.5 to 2 e of t dt. So, here it is integral 1.5 to 2 1 into dt, which is equal to 2 minus 1.5. You will get as 0.5. So, 50% of the fluid spends the time between 1.5 to 2 minutes. Okay. Now, let's get on to question number 4. The second order aqueous reaction A plus B gives R plus S is run in a large tank reactor with volume equal to 6 meter cube. And for an equimolar feed stream, Ca naught is equal to Cb naught, the conversion of reactants is 60%. Unfortunately, agitation in our reactor is rather inadequate, and tracer tests of the flow within the reactor give the flow model sketched in the figure below. What size of the mixed flow reactor will give equal performance of our present unit? So they have given a tank reactor. Okay, this is some stir tank reactor where equimolar feed stream of A and B enters the reactor with the second order reaction. So A plus B gives R plus S. The total volume of the reactor is 6 meter cube. Okay, but it is not an ideal reactor, and there is a non-ideality occurring in the reactor. So the non-ideality from the figure, we can identify that it happens in two ways. One is there is some bypassing. So 0.2 from the total volumetric flow only 80% of the volumetric flow rate of the feed enters the reactor, and 20% it just gets bypassed. And also, if we consider the reactor, though the reactor volume is 6 meter cube, 4 meter cube is a dead volume reactor, and only 2 meter cube is the active reactor. Now we have to find out the volume of a mixed flow reactor which gives the equal performance of our present unit. That means we have to find out what will be the volume of a mixed flow reactor or a CSTR which gives the same conversion as that of the given reactor. So what is the conversion of this reactor? It is 60%. That means X is 0.6. Right. So we have to find out what volume of a MFR is required for this 60% conversion. Okay. MFR in the sense the ideal CSTR reactor. Now let's proceed with how to solve this question. So given a second order reaction, A plus B gives R plus S with Ca naught is equal to Cb naught. So we can consider minus Ra, the reaction rate is equal to K into Ca square. Right? Because Ca naught is equal to Cb naught, so Ca equal to Cb we can consider. So A plus B can be taken as 2A gives R plus S also. So that is why you have minus Ra is equal to K into Ca square. They have given that there is a tank reactor and the total volume of the reactor is 6 meter cube. However, so this part of it, 4 meter cube is a dead volume. That means the active reactor is only 2 meter cube. That is also they have given. This is what is getting stirred properly and the reaction happens in this zone only. Okay. And they have given there is a split in the volumetric flow rate also. So, 20% of the volumetric flow rate of the reactants gets bypassed. Right. And only 80% of the volumetric flow rate enters into the reactor. Whereas here the output, again you will get the same volumetric flow rate as the overall input. Okay. Now the volumetric flow rate into the active reactor is, so now let us consider the volumetric flow rate V to be 100 meter cube per minute. So the actual volumetric flow rate that gets into the active reactor is 0.8 times of V, which is nothing but 0.8 into 100, that is 80 meter cube per minute. Okay. Now volumetric flow rate of the bypass is 1 minus 0.8, that is 0.2 into V, which is 20 meter cube per minute. And then let us also assume that Ca naught is equal to Cb naught is equal to 100 mole per meter cube. That is the concentration of A and B in the feed stream is 100 mole per meter cube. And the conversion X is 0.6. They have also given the conversion of reactants is 0.6. That is this output conversion from here where this arrow is pointing out is 60%, that is 0.6. Okay. The active reactor volume where the reaction occurs is 2 meter cube. That also is given. We can find it out from the representative figure. Now, how to proceed with this? We have to, let us assume a mole balance at 0.2. Okay. So, mole balance at 0.2 is, so this 80% of the volumetric flow rate into some concentration Ca1. From here some concentration. So so some concentration Ca1 after the reaction comes out of this, and then it mixes with the concentration from this point which is getting bypassed and then comes out as Ca2. One more consideration we have to consider is that though the volumetric flow rate is split up, the concentration here also, what is entering the reactor is also Ca naught and Cb naught. Okay. So, here whatever is entering the reactor is at this point, at point number 1, which is entering the reactor is Ca naught. The concentration of A is Ca naught, which is 100 mole per meter cube, and concentration of B is also Cb naught, which is 100 mole per meter cube. And then also which is getting bypassed. Here also the concentration of A and B are not changed. So it is Ca naught equal to Cb naught equal to 100 mole per meter cube. So that is how we are going to write the mole balance. Okay. So once it comes out of the reactor, here this Ca naught and Cb naught will get converted to some Ca1 and Cb1. So Ca1 equal to Cb1. Okay, that is also an assumption. Okay, since Ca naught is equal to Cb naught. Okay, so here 0.8 into V at this point of mixing point, we can take the mole balance. So from here 0.8 V volumetric flow rate comes out with a concentration of Ca1, plus from this point, from the bypass point, whatever moles we will get, it is 0.2 into V into Ca naught. Okay, and that will come out from the overall output of the reactor, where the overall output is here again the volumetric flow rate is V, and the concentration becomes, so the combination of these concentrations, which is Ca2. Okay, and Ca2, it's been given that the conversion at this point 2 is, the final concentration that is coming out is the conversion is 60%. That means the Ca2 is 1 minus x into Ca naught, which is 1 minus 0.6 into 100, that is 40 mole per meter cube. Okay, this is what is coming out. Now the mole balance becomes, we can cancel V here. So 0.8 into Ca1 plus 0.2 into 100, because here again Ca naught is equal to 100 is equal to 40. So we will end up, so substituting the values and rearranging. So 0.8 Ca1 is equal to 40 minus 20, which is equal to 20. So we will end up with Ca1, the concentration coming out of the reactor, where the reaction has taken place, is 25 mole per meter cube. That is what is the concentration of A and B that is coming out of the reactor. Okay, before it enters the point 2. Okay, mixing point 2. Okay, now we have to consider the active 2 meter cube real reactor as ideal CSTR. Okay. So this part alone is an ideal CSTR. And the performance equation of this portion is given by V by V, where small v is the volumetric flow rate and capital V is the volume of the reactor, is equal to Ca0 minus Ca1. So we are just doing a performance equation for this part of the CSTR alone. That is a 2 meter cube volume of CSTR alone. So it is Ca0 minus Ca1 by K into Ca1 square. So in this equation, we have the value of V, which is 2 meter cube, and then the volumetric flow rate in this part is 80 meter cube per minute, and then Ca0 is again 100 and Ca1 is 25 divided by K, we don't know what is the reaction rate constant, into Ca1 square, which is nothing but 25 square. So you will upon rearranging, you will get the value of K is equal to 4.8 meter cube per mole minute. Okay, since it is a second order reaction, the unit is meter cube per mole minute. Now, the next part. Now we have to identify what is the volume of an ideal CSTR that gives the same conversion as this entire system. And so the conversion should be 0.6 and the output concentration should be 40 mole per meter cube and the volumetric flow rate should be 100 meter cube per minute. So let us find out what will be the volume. So again, performance equation of the CSTR. So V by V0 is equal to Ca0 minus Ca2 divided by K into Ca2 square. Right? So we have to find out V, and then V0, the volumetric flow rate is again 100, is equal to Ca0 is 100 and Ca2, whichever is coming out, the final output concentration is 40 mole per meter cube, because the conversion is 60%. Okay, divided by K into Ca2 square. So K is 4.8, which we have found out because your reaction rate constant is not going to change with the reactor. It is the intrinsic reaction rate constant. It is particular to a particular reaction. Okay, so it is 4.8. Okay, into 40 into 40 square. So you will end up with V is equal to 0.78125 meter cube. So volume of the mixed flow reactor or an ideal CSTR with equal performance as a given reactor is 0.78125 meter cube. That means we can from this we can observe that if we go for an ideal CSTR or ideal mixed flow reactor to give a same performance of 60% conversion for this second order reaction of A plus B giving R plus S with Ca0 equal to Cb0 and a volumetric flow rate of 100 meter cube per minute, you will require a very small reactor compared to this reactor. This reactor takes up a volume of 6 meter cube, whereas the ideal mixed flow reactor, it requires to only 0.78 meter cube for giving the same performance. Okay, so a lot of volume is getting space or volume is getting wasted because of the non-ideality that is being induced in the reactor. Okay, now let us go on to sorry, here again it is week 11. It's not week 10, it's week 11. So the next question is, dispersed non-coalescing droplets with Ca0 equal to 2 mole per liter reacts as per the following way. So A gives R with a second order mechanism. So minus Ra is equal to K into Ca square, where the reaction rate constant is 0.5 liter per mole minute as they pass through a contactor. Now we have to find the average concentration of A remaining in the droplets leaving the contactor if their RTD function is given by E of t is equal to 0.5 minute inverse for time between 1 to 3 minutes. So there are some non-coalescing droplets in a dispersed non-coalescing droplets in a reactor. Okay, and it is having some reactant A with an initial concentration of 2 mole per liter, and it reacts as per a second order mechanism where minus Ra is given by K into Ca square. They have also given what is the value of K, which is equal to 0.5 liter per mole minute. And they have also given RTD function for this reactor where E of t is 0.5 minute inverse for time between 1 and 3 minutes. Okay, they have asked us to find the average concentration of A remaining in the droplets leaving the contactor. That means, so given non-coalescing droplets. So therefore we can consider segregated model with each droplet acting as a batch reactor. So Ca0 they have given 2 mole per liter, and then A gives R, and minus Ra is equal to K into Ca square, where K is equal to 0.5 liter per mole minute. So the average concentration can be found out from this formula, right, for the segregated model, right? So segregated model, we can find out the average concentration using this formula. So where Ca bar is the average final concentration divided by Ca0, which is the initial concentration, is equal to integral 0 to infinity Ca by Ca0 for each element or little batch of fluid of age t multiplied by the exit age distribution, that is E of t into dt. Okay. Now for a second order batch reaction. So for a second order reaction for a batch reactor, because they have given the reaction is following a second order mechanism, right? Because Ra is minus Ra is K into Ca square. So that means it is a second order mechanism. So Ca by Ca0 is given by 1 by 1 plus K into Ca0 into T, right? Now substituting that value of Ca by Ca0 into the expression of the average concentration. So Ca bar by Ca0 is equal to integral 0 to infinity 1 divided by 1 plus K into Ca0 into T into E of t into dt, right? Now E of t they have given 0.5 minute inverse for time 1 to t. That means here again we have to split the integral. So for integral 0 to 1, again the E of t value is to be taken to be 0 because they have given the value of E of t is 0.5 only for time between 1 and 3 minutes. So that means integral 0 to 1 E of t will be between integral 0 to 1 E of t will be 0, and then similarly between 3 to infinity E of t will be 0. So the valid integration will be from integral 1 to 3 1 by 1 plus K into Ca0 into T into E of t dt, right? So substituting the values, all the values, what you will get? So you will have integral 1 to 3, 1 divided by 1 plus K, the value of K, the reaction rate constant is 0.5, and multiplied by Ca0. Ca0 they have given us 2 into T multiplied by E of t. E of t is 0.5 for the range of 1 to 3. That is also given. So 0.5 into dt, which is nothing but you will get integral 1 to 3, 1 divided by 1 plus t into 0.5 dt. So integration of 1 divided by 1 plus t is ln of 1 plus t. Okay. So substituting that, and then between the limits of 3 to 1. So you will get concentration Ca bar, that is average concentration Ca bar by Ca0 is equal to 0.5 into ln of t plus 1, substituting the value of 3. So you will get 3 plus 1, that is 4. So ln of 4 minus 0.5 into ln of 1 plus 1, that is ln of 2. So substituting the values, you will get the value of Ca bar by Ca0 is equal to 0.347. So what will be the value of Ca bar? Ca bar is the average concentration of A that is coming out of the reactor. So Ca bar is equal to 0.347 into Ca naught, which is equal to 0.347 into 2, that is equal to 0.694 mole per liter. So that is what is the average concentration of A remaining in the droplets leaving the contactor. Okay. We can also find out what is the average conversion. So Xa bar is equal to 1 minus Ca bar by Ca naught. So we have the value of Ca bar by Ca naught as 0.347. That means Xa bar is equal to 1 minus 0.347, that is equal to 0.653. That means here the conversion is about 65%. Okay. This is what is the conversion in this reactor using a segregated model. Alright. So that's it with the session. Thank you.